Hello friends, welcome to my second lecture on joint probability distribution. Let us first consider the discrete case of two random variables. So, in the case of discrete random variable xy with probability function fxy, the probability that x takes the value x and y is arbitrary is given by f1x equal to probability that x takes the value x, y is arbitrary. So, we take the sum of the function fxy over all the values that the random variable y takes. This will give you the marginal distribution or marginal density of x with respect to the given two dimensional distribution. Now, in the case of cumulative distribution function, we have f1x equal to probability that x less than or equal to x and y arbitrary, which will be sigma f1 x star, where x star is less than or equal to x. So, we will take the sum of the marginal density function over all values of x star which are less than or equal to x to get the cumulative distribution function of x with respect to the given two dimensional distribution. In the case of the marginal density function of y with respect to the given two dimensional distribution, we have f2y equal to probability that x is arbitrary, y equal to y. Okay. This is defined in a similar manner as the case of marginal density function or marginal distribution of x with respect to the joint distribution xy. So, probability that x is arbitrary, y is equal to y is sigma fxy, where x sigma is taken over the values of x, the values that x takes. Okay. So, this is called the marginal density or marginal distribution of y with respect to the two dimensional distribution. The cumulative distribution function of this distribution, that is cumulative distribution function of y with respect to the given two dimensional distribution, is f2y equal to probability that x is arbitrary, y is less than or equal to y. Here we take the sum of the marginal density function over all values of y star that are less than or equal to y. Both the marginal distributions you can see of the discrete random variable xy are discrete. Now, in the case of a continuous random variable xy with density function fxy, we may consider x less than or equal to x, y arbitrary, or x less than or equal to x minus infinity less than y less than infinity. The corresponding probability function, okay, is given by f1x equal to the corresponding probability will be f1x equal to p x less than or equal to x minus infinity less than y less than infinity. This is integral over minus infinity to x, integral over minus infinity to infinity f x star by dy dx star. This is the cumulative distribution function in the case of the cumulative distribution function of x with respect to the joint distribution xy. Here this integral over minus infinity to infinity f x y dy is f1x, which is the marginal density function of x with respect to the joint distribution. Okay. So, using this marginal density function f1x, we can write the cumulative distribution function f1x as integral over minus infinity to x f1 x star dx star, where f1x is called the marginal density and capital F1x is called the cumulative distribution function of the marginal distribution of x. So, this f1x is called the marginal density or marginal distribution, and f1x the cumulative distribution function of the marginal distribution of x with respect to the given continuous distribution. Now, in a similar manner we can define the marginal density function or marginal distribution of y with respect to the joint continuous distribution xy and the corresponding cumulative distribution function. So, the marginal density function of y with respect to the joint distribution will be given by f2y equal to integral over minus infinity to infinity fxy dx. It is called the marginal density, okay, and the corresponding cumulative distribution function is f2y equal to integral over minus infinity to by f2 by star dy star, which is equal to integral over minus infinity to y. Putting the value of f2 by star here, we get integral over minus infinity to infinity f x y star dx dy star. Okay, so this is called the cumulative distribution function of the marginal distribution of y with respect to the given two dimensional distribution, and both you can see the marginal distributions, that is f1x, this f1x, okay, this one, and the next one f2y, okay, they are continuous, you can see. Okay, let us consider the following example. The following table gives the probability distribution of x and y. Okay, so this is by means these values are of by equal to 1, this is by equal to 2, and here we have x equal to 1, x equal to 2, x equal to 3. Okay, so we want to find the marginal density function of x first of all. Okay, marginal density function of x means we want to determine fxx. Okay, marginal density function or marginal distribution of x. Okay, so here you can see x takes the values 1, 2, 3. Okay, by takes the value 1, 2. Okay, so fxx. Okay, fxx we have to determine. Fxx will be given by sigma fx by equal to 1 to 2. Okay, yeah. So this will be fxy and fyy. This is marginal density function of y. So f by y will be equal to sigma fxy, x varies from 1 to 3, okay, because x takes the values 1, 2, 3. Now you can see here when so this is fxx will be found for x equal to 1, 2, 3, x equal to 1, 2, 3, okay, and fyy will be found for y equal to 1, 2. Okay. Now you can see here if you sum the column entries, okay, if you sum the column entries, then you get the value of fxx for x equal to 1. Okay. So here you write this is fxx. Okay. You can see here in this table. So fxx, when x equal to 1, fxx will be summation over all the values of y equal to 1 to 2. So this is 0.1 plus 0.2, that is 0.3. Okay. When x is equal to 2, x equal to 2, okay, the values of y are 1 for 1 and 2 are 0.1 and 0.3. So let us sum over the values of y. So it is 0.4. Okay. And then when x is equal to 3, the values of fxy are, for y equal to 1 it is 0.2, for y equal to 2 it is 0.1. So we have 0.3. Okay. So we can say the marginal density function of x, the part A. Okay. So we have values of x here and we have fxx here. Values of x are 1, 2, 3. And the values of fxx are 0.3, 0.4, 0.3. Okay. So this is the answer for the part A. This is marginal density function of x. Now part B. So now we want to find marginal density function of y with respect to the joint distribution. So we have this. So this is our y is taking values 1 and 2. Okay, we want f by y. Okay, f by y. Okay. So now what will happen? F by y is summing of the values of fxy for x equal to 1 to 3. X goes from 1 to 3. So we now take the sum of rows entries in the rows. Okay. So we have this. So this is f by y. Okay. When y is equal to 1, okay, you can sum the entries 0.1, 0.1, 0.2. So 0.1, 0.1, 0.2 is 0.4. Okay. Summing of the values of fxy, okay, when x runs from 1 to 3, means you take the sum of the entries in the row for y equal to 1, and then for y equal to 2 you take the again the sum 0.2, 0.3, 0.1, so 0.6. So we have 0.4 and this is 0.6. So, this is probability density function of marginal density function of y, and this is marginal density function of x. Let us now consider, we have considered just now a discrete case of two discrete random variables. Let us consider now a continuous case, continuous joint distribution of two continuous random variables. So, the joint density function of two continuous random variables x and y is given by f x y equal to c x y. X varies from 0 to 4, okay, y varies from 0 to 1 to 5, then f x y c x y and 0 otherwise. Okay. So, we have to determine the value of the constant c first. Okay. We know that f x y is the joint density function. So, integral over minus infinity to infinity, integral over minus infinity to infinity f x y dx dy will be equal to 1. Okay. This implies that by the definition of f x y, integral 0 to 4, integral 1 to 5, c x y dx dy equal to 1, because f x y is 0 elsewhere. Okay. Now, c is a constant, we integrate with respect to x to get x square by 2, and it is 0 to 4, and then we have integrated, when we integrate by, we get by square by 2, integral over 1 to 5, okay, this is equal to 1. Okay. So, this implies c times 16 by 2 means 8, okay, and then we have 25 by 2 minus 1 by 2. So, 24 by 2, that means 12. So, we have c equal to 1 by 96. Okay. So, this is the value of the constant c. Now, let us find the probability that x is greater than or equal to 3, y is less than or equal to 2. Okay. So, probability that x is greater than or equal to 3 and y is less than or equal to 2 will be given by integral over 3 to infinity, okay, x varies from 3 to infinity, y varies from minus infinity to 2, f x y dx dy. Okay. So, by the definition of f x y, it is only c x y over the interval 0 to 4 for x and 1 to 5 for y, elsewhere it is 0. So, this integral will become the integral from 3 to 4 for x, because when x is greater than 4 it is 0, and for y it will be replaced by 1 to 2, because if it is x y is less than 1 it is 0. Okay. So, c x y dx dy. Okay. So, let us now calculate it 3 to 4, 1 to 2. So, we have p x greater than or equal to 3, y less than or equal to 2 is given by this integral. Okay. So, we integrate 1 by 96 into x square by 2, integral over the limits are 3 to 4, then we have y square by 2, limits are 1 to 2. So, this gives you 1 by 96, and we have here 16 by 2 means 8 minus 9 by 2, and we have here 4 by 2 means 2 minus 1 by 2. Okay. So, this is equal to 1 by 96, and then we have 16 minus 9. So, 7 by 2, and we have here 3 by 2. Okay. So, 3 when cancels with this we get 3 2 3 3 9 and 3 2 6. So, this is 7 by 128. Okay. So, this is the probability when x is greater than or equal to 3, y is less than or equal to 2. Now, find the marginal distribution function of x. So, we have to find the marginal density function of x. Okay. Now, marginal density function of x is given by is equal to f x x, and this is given by integral over minus infinity to x, okay, fxy, no, it is given by integral of minus infinity to infinity fxx equal to integral over minus infinity to infinity fxy dy, okay. Yeah, we have to, because fxx is probability that x takes the value x and y is arbitrary. So, this is integral over y varies from 1 to 5, okay, elsewhere it is 0 for y, fxy is 0. So, 1 to 5, okay, and we have a cxy dy, okay. So, this is c is 1 by 96 into x into y square by 2, and we have limits 1 to 5, okay. So, x by 96 and we have 25 by 2, when you put y as 5, 25 by 2 minus 1 by 2. So, we have 12, okay. So, 12 8 is 96. So, we have x by 8, okay. So, if x lies in the interval 0 to 4, okay, if x lies in the interval 0 to 4, then fxx is x by 8, okay. So, thus fxx is equal to x by 8 when 0 is less than x less than 4 and 0 elsewhere, because if your x does not lie in the interval 0 to 4, okay, fxy will be 0, okay. So, this is for 0 less than x less than 4. So, this is the marginal density function of x, okay, for example 2. Now, let us discuss independence dependence of random variables. The random variables x and y of two dimensional distribution xy with distribution function fxy, cumulative distribution function fxy are called independent, okay, if fxy equal to f1x into f2y, it holds for all xy, otherwise these variables are said to be dependent. Suppose that x and y are both discrete, okay, are both continuous, then x and y are independent if and only if the corresponding probability functions are densities f1x and f2y satisfy fxy equal to f1x into f2y for all xy. For example, you consider the case of random variables x and y, where x denotes the number of heads on a dime, okay, and y denotes the number of heads on a nickel, okay. Then when you toss a dime and a nickel, okay, and you x and there x denotes the number of heads on the dime and by the number of heads on the nickel, then they will assume values 0 and 1, okay. And so, they are both dependent, as they are both independent. The notion of independence and dependence may be extended to n random variables of an n dimensional distribution. In a similar manner, we can extend it. So, here the number of heads, if you calculate the number of heads on a dime and it denoted by x, and number of heads on a nickel that denoted by y, then either head will come, then number will be 1. If x head does not come, then the value will be 0, okay. So, number of heads will be either 0 or 1, okay, and they are independent events. So, this is the case where random variables x and y are independent to each other. Let us look at the joint probability distribution of x and y. Fxy equal to 1 over 27 times 2x plus y, x equal to 0 1 2, y equal to 0 1 2. Find the marginal distribution of x and y. So, let us first find the marginal distribution of x. So, fxx let us find. Fxx is sigma y equal to 0 to 2 fxy, okay, and x takes the values 0 1 and 2, okay. So, let us form the table for fxx. You can see we will have to first form the table for all x and y, okay. So, let us say like this. This is suppose x and this is y, okay. So, y takes value 0 1 2, okay. X also takes value 0 1 and 2. Okay. So, when x is 0, y is 0, x is 0, y is 0, f 0 0 equal to 0. So, this is 0. Okay. When x is 0, y is equal to 1, x is 0, y equal to 1, so it is 1 by 27. When x is 0, y is equal to 2, it is 2 by 27. Okay. When x is equal to 1, y is 0, 2 by 27. When x is 1, y is equal to 1, it is 3 by 27. When x is 1, y is 2, it is x is 1, y is 2, 4 by 27. Okay. When x is 2, y is 1, y is 0. Okay. So, it is 4 by 27. When x is 2 and y is 1, so it is 5 by 27. And when x is 2, y is 2, so it is 6 by 27. Okay. Let us total, make the total row wise. Okay. So, when you row wise you consider the total, okay, then what will happen? You are summing over fx by for y equal to 0, 1, 2, okay, x remains fixed. Okay. Suppose x is 0. Okay. So, fx0 will be sigma y equal to 0 to 2, okay, f0 y. Okay. That means f0 0 plus f0 1 plus f0 2. So, this is 3 by 27. Okay. And when fx1 you want to find, fx1 will be sigma y equal to 0 to 2 f1 by. Okay. So, 2 3 5 4 9 9 by 27. Okay. And then fx2. Similarly, fx2 will be 4 5 9 9 6 15 by 27. Okay. So, we have 3 plus 9 12, 12 plus 15 27 by 27. So, sum of fxx sum of fxx when x varies from 0 to 2 must be equal to 1. Okay. That is a check. So, this is fxx. Okay. Similarly, we can find f by y equal to sigma x equal to 0 to 2, okay, and we have fx y. Okay. So, f by 0, okay, f by 0 is sigma x equal to 0 to 2 f, okay, this. Okay. So, when you take x equal to 0, we have f0 0, when you take x equal to 1, we have f1 0, when you take x equal to 2, we have f2 0, that is column sum. Okay. So, 0, 2 by 27, 4 by 27, so 6 by 27, okay, and f by 1 similarly, okay, column sum. So, 1 plus 3 plus sum of the entries in the column. So, 1 plus 3 4, 4 plus 5 9 by 27, and f by 2 equal to, you can see 2 plus 4 6 plus 6 12 by 27, and sum of the values of f by y for y equal to 0 1 2 must be equal to 1. So, this is 6 by 27, this is 9 by 27. So, 15 by 27 plus 12 by 27. So, 27 by 27, that is equal to 1. So, conditional marginal distribution of y, we have this table. Y here, f by y here. Okay. Y is taking value 0 1 2. Okay. When y is 0, it is 6 by 27. When y is 1, it is 9 by 27. When y is 2, it is 12 by 27. Okay. So, this is marginal density function of y with respect to the joint distribution. This is marginal density function of x, this one, fxx equal to, you can write it in the form of the table. For 0 it is 3 by 27, for 1 it is 9 by 27, for 2 it is 15 by 27, like this. Okay. So, this is marginal density function of x, this is marginal density function of y. Okay. Are x and y independent random variables? Now, as we have seen in the definition of independence, x and y will be independent random variables if fxy is equal to fxx. The joint density function must be equal to the product of the marginal density functions. Fxy must be equal to fxx into fyy for all xy belonging to 0 1 2 for all xy where x takes values from 0 1 2 and 0 1 2 and y takes value 0 1 2. Now, let us see here we can notice that f00 you can see f00 here is from the table you can see when x is 0 y is 0 it is 0. Okay. So, this fx0 f00 when x equal to 0 y equal to 0 is 0. Okay. What is the value of fx0? Fx0 equal to 3y27. Okay. What is the value of fy0? It is equal to 6/27. Okay. So, fx0 into fy0 is equal to 18/27 into 27. Okay. So, we get fx0 into fy0. Okay. 3/27 into 6/27. Okay. So, this is 1/9 and this is 2/9. So, this is 2/81, okay, which is not equal to 0 and 0 is the value of f00. So, f00 is not equal to fx0 into fy0, okay, and therefore, x and y are not independent. Okay. X and y will be independent provided fxy will be equal to fxx into fyy for all xy. Now, we can see one more thing f22, let us check one more for one more pair when x is 2 y is 2. So, f22 is how much here you can see f22 is 6/27. Okay. So, this is f22 the density function for the joint distribution when x is 2 y is 2 6/27. What is fx2? Fx2 is equal to 15/27. 15/27 means 5/9, okay, and f/2 will be equal to 12/27. f/2. So, 4/9. Okay. So, 5/9 into 4/9 is equal to 20/81. Okay. So, f22 is equal to 6/27 and this is not equal to fx2 into f/2 which is equal to 20/81. Okay. So, there is one more pair when x is 2 y is 2 fxy is not equal to fxx into fyy. So, x and y are not independent random variables. Let us take now the case of continuous random variables x and y. So, the random variables x and y have the joint probability density function given by fxy equal to 6 times 1 minus x minus y when x is greater than 0, y is greater than 0, x plus y less than 1 and 0 otherwise. So, let us see in which part of the xy plane fxy is non-zero. So, this is the part, this is 1, this is 1, this part, okay. This is x plus y equal to 1, this is x axis and this is y axis. Okay. So, x is greater than 0 here, y is greater than 0 and x plus y is less than 1. Now, we want to find the marginal density function of x and marginal density function of y. So, fxx we have to find fxx equal to when x will be greater than 0, y is greater than 0. So, fxx is integral over minus infinity to infinity, okay, fxy dy. Okay. Now, In this region f x y is given by 6 times 1 minus x minus y. So, this will be integral over y varies from, we have to integrate over y, x remains constant. So, we have to take a vertical strip. Along the vertical strip x is constant, y varies, and y varies from 0 to 1 minus x. Okay. So, y varies from 0 to 1 minus x, and we have 6 times 1 minus x minus y dy. Okay. And this is the case when x lies between 0 and 1. If x lies elsewhere, f x y will be 0. So, this is equal to 6 times x minus x square by 2 minus x y, and when we put the limits y equal to 0 to y equal to 1 minus x, what we get is 6 times x minus we are integrating with respect to y. So, we should write here y minus x into y minus y square by 2. Okay. So, y is equal to 1 minus x. So, we have 1 minus x here, and then x times 1 minus x, and we have minus 1 minus x whole square by 2. Okay. When y is 0, this is 0. Okay. So, this is how much we can take 1 minus x common. So, 6 times 1 minus x, and what we get inside 1 minus x, okay, 1 minus x minus 1 minus x by 2. Okay. So, 1 minus x by 2, that is the value of the expression inside the bracket. So, this is 3 times 1 minus x whole square. So, this is the f x x, the value of f x x when 0 is less than x less than 1. So, we can write the marginal density function here, marginal density function as f x x equal to 3 times 1 minus x whole square when 0 is less than x less than 1 and 0 otherwise. Okay. Now, we let us find the other marginal density function, that is marginal density function of y. Okay. When we want to find the marginal density function of y, now what will happen? We will integrate f x y with respect to x, keeping y fixed. Okay. So, y is fixed along the horizontal strip. Okay. So, x is when y is fixed, x varies from 0 to 1 minus x. Okay. X varies from 0 to 1 minus y. So, we have this f by y equal to integral over 0 to 1 minus y f x y dx. Okay. So, this is 0 to 1 minus y and 6 times 1 minus x minus y dx. Okay. So, again what we will have? We will have the integral as 6 times x minus x square by 2, okay, minus x into y, right, and the limits are 0, 1 minus y, and the values of y vary from 0 to 1, okay, because we have this region and we are taking a horizontal strip in this region. So, y is fixed here, y varies from 0 to 1. Okay. So, this will be again 6 times 1 minus y minus 1 minus y whole square by 2 minus y into 1 minus y. So, what we will get? This is 6 times 1 minus y, we can take common, and then what we will get? 1 minus y by 2 minus y, okay, which is 3 times 1 minus y whole square, 0 less than y less than 1. So, f by y equal to 3 times 1 minus y whole square, 0 less than y less than 1 and 0 otherwise. Okay. Now, we have to answer whether the variables x and y are independent or not. So, we have to see f x y must even if they are independent, f x y must be equal to f x x into f by y, f by y. Okay. So, let us check this, let us check whether it is true or not. Okay. So, f x y is equal to, we are given that f x y is equal to 6 times 1 minus x minus y when x is greater than 0, y is greater than 0 and x plus y is less than 1 and 0 otherwise. Here what is happening is f x y, we have seen f x y is equal to 6 times 1 minus x minus y, x is greater than 0, y is greater than 0, x plus y less than 1, okay, and 0 otherwise. And what we find is that f x x into f y y, okay. This is equal to 3 times 1 minus x whole square into 3 times 1 minus y whole square. So, 9 times 1 minus x whole square into 1 minus y whole square when 0 is less than x less than 1, 0 is less than y less than 1, okay, in this region and 0 otherwise. Okay. So, in the common portion, this portion, see when 0 is less than x less than 1 and 0 less than y less than 1, we are here, okay, in this square, okay, and this region is a part of this, okay. So, over this region where x is greater than 0, y is greater than 0, x plus y is less than 1, f x y 6 times 1 minus x minus y, while f x x into f y y is 9 times 1 minus x whole square into 1 minus y whole square. So, they are not equal, okay. So, f x, so it turns out that f x y is not equal to f x x into f y y when x is greater than 0, y is greater than 0 and x plus y is less than 1, okay. So, they are not independent, okay. So, x and y are not independent. Okay. Yeah. So, we have found the marginal density function of x and y, and also we have seen that x and y are not independent. So, with this I would like to end my lecture. Thank you very much for your attention.